Greetings, and thank you for listening to this presentation. I am Jeffrey Pierce, President of JP Innovations, LLC. This presentation will discuss our work for the Navy to develop a high-energy, long-pulse laser system suitable for use as a directed energy source. First, a brief overview of our company. JPI designs and manufactures custom laser systems for the Department of Defense and also for commercial applications, covering a wide range of optical parameter space. We have been in business for 24 years and have designed, manufactured, and delivered many different types of laser, optical, and nonlinear optical systems. These systems include flash lamp pumped and diode pumped lasers, custom optical parametric oscillators, fiber-coupled laser systems, and many different systems with customized output wavelengths. Through the years, we have performed a number of successful SBIR programs, including pulsed blue lasers, and the current program developing high-pulse energy lasers for ship protection. The Navy, Air Force, and Army have been developing directed energy weapons for many years. The photograph shows one such system that was deployed on the USS Ponce in 2014 to demonstrate the utility of a directed energy system. The approach that JP Innovations has taken to develop a laser suitable for a directed energy system is a flash lamp pumped neodymium glass laser, which has many advantages over the diode pumped fiber lasers that have been pursued for more than 2 decades. The goals for our development program are described in summary in the third bullet item on this slide. The most important feature of our laser system is pulse energy, up to 1 kilojoule with a pulse duration around 4 milliseconds, at the full width half maximum, which yields a peak power of 500 kilowatts at the maximum of the temporal Gaussian pulse. Such high power delivers greater materials effects at significant range, dramatically improving the utility of a directed energy weapon system. This SBIR program was originally intended only to develop reduced size, weight, and power swap pulse power components suitable for a high-energy laser system as goals for operational use and improvement of a directed energy source. The program goals as described in the solicitation are shown in the second bullet item on this slide, with benchmarks for swap reduction shown for a complete program through Phase 3. However, JP Innovations chose to develop a complete high-energy laser system under this SBIR Phase 2 project. In addition to vastly reducing the size and weight of the pulse power electronics, which the solicitation called for, we have also developed a high-efficiency flash lamp pumped laser system. There is a demonstration laser system of Navy design that is currently operating at China Lake NAWC called Viper, which typically achieves approximately 1.6% conversion from pump energy stored on the capacitor bank to laser optical output energy. JP Innovations laser has achieved an output conversion efficiency of 3.77%, which is an improvement of 236%. Further modifications planned or underway are expected to increase this output efficiency metric to over 4%. This slide gives a summary of our Phase 2 program results to date. The first bullet item of this chart describes all of the components of the deliverable laser system. We are currently building this system, which will have an output pulse burst of 8 pulses with up to 1 kilojoule of energy per pulse, for a total of 8 kilojoules. This output will be delivered by 4 lasers with 2 pulses each, and the photograph at the bottom of this slide shows one of these laser assemblies. To make our laser insensitive to environmental conditions, JP Innovations has developed an extremely stable optical resonator structure, which holds the resonator mirrors. This feature enables deployment of our system in any environment, including land, sea, and airborne applications. The third bullet item on this slide summarizes the dramatic improvement in swap that our pulse power technology has made relative to the Viper laser system. This was the primary goal of the SBIR program, and JP Innovations has already vastly exceeded the Phase 3 goals set out in the original solicitation by our performance on this Phase 2 project. Here is a features, advantages, and benefits table that compares and contrasts our technology primarily to continuous wave, diode-pumped fiber laser systems. Fiber laser systems have struggled to reach 100 kilowatts of output power, whereas we have already achieved a peak of 500 kilowatts in a high-energy, long pulse from a single low-cost device. Our laser system can deliver a burst of these high-energy pulses in a fraction of a second, and the output pulse energy can be scaled to even higher values relatively easily. Output peak power of up to 1 megawatt per pulse is readily achievable, which will deliver very effective materials interactions downrange in real operating scenarios. Finally, our laser approach will produce effective directed energy systems at a small fraction of the cost of high-power fiber laser systems. This slide details the current status of our SBIR Phase 2 program. We are presently assembling and testing all of the deliverable hardware, including the control system. After all of the subsystems have been tested, they will be delivered, and then the complete system will be integrated in the Viper Lab at China Lake NWC. The performance of the full laser system will be characterized at that time. After this system is operational at China Lake, the technology readiness level will be approaching 6. However, presently there is no program of record into which this technology can be incorporated. As such, China Lake NWC has requested that a sequential Phase 2 contract be awarded to JP Innovations to continue the system development by making improvements to output beam quality, pulse burst rate, and further reductions in system swap. We have recently submitted the requested proposal for evaluation and award. JP Innovations has conducted a preliminary design study that shows our system can be integrated into an aircraft fuel pod, enabling airborne operations and vastly extending the effective range of ship protection that can be achieved. The SolidWorks model image at the bottom of this slide shows a full 4-laser, 8-pulse system inside of a pod, and there still is sufficient room for the beam director, cooling, and power distribution components of a complete pod laser directed energy system. The Department of Defense has been pursuing directed energy weapons for many years. The Navy and Air Force have conducted most of the efforts. JP Innovations has conducted this program with Navy sponsorship. Our TPOC has indicated that the Air Force also has interest in this technology. Regarding commercial applications, the most appropriate application for this technology is in the field of shock peening. This is a process of surface treatment of complex metal surfaces. The effect of the laser beam on the surface of the part causes compaction of the atoms on the surface, hardening the surface for complex parts such as aircraft turbine blades. This process relieves machining stress and hardens the parts against difficult operational environments. Using this technology, JP Innovations could bring a shock peening system to market with excellent performance at a much lower price compared to systems currently available. Transition support includes receiving the expected sequential Phase 2 contract, for which we have submitted a proposal. That program will enable JP Innovations to make significant improvements to the laser system to enhance its suitability as a directed energy laser source. This will demonstrate tremendous advancement of the technology since the Phase 1 award. After that, if a program of record is set up and the technology can transition into a Phase 3 program, JP Innovations would team with a large defense contractor to pursue system deployment. We are open to all reasonable business approaches to transitioning this technology to the Navy. Thank you very much for your time and attention. Should you be interested to learn more about the capabilities of our technology, or if you have custom laser system development needs of your own, please do not hesitate to contact me directly.